So we spend, an enormous amount of capital and engineering effort trying to protect modern infrastructure from losing power.
Oh, absolutely. The investment is staggering.
Right. Like you look at a tier one data center or a regional trauma hospital, and the sheer volume of equipment dedicated just to keeping the lights on is wild.
Yeah, and it creates this profound engineering paradox that we deal with every day.
Because sitting in the basement or, out in the yard is a piece of machinery holding hundreds of gallons of highly flammable liquid.
Exactly. Operating at temperatures that can literally melt aluminum right next to the building you're trying to protect.
Welcome to the deep dive. Today, we have a clear mission for you. We are decoding NFPA 37.
The standard for the installation and use of stationary combustion engines and gas turbines.
Yeah, that's the one. And we are pulling from a really great array of technical sources today, including Consulting Specifying Engineer magazine, the Anvil Fire blog, some federal EPA guidelines, and real-world case studies from EPC land.
And our mission here is to translate this dense material into a functional design playbook for you.
Right. Whether you are a facility owner staring at a set of blueprints or a fire protection engineer trying to get a design through plan review, we're unpacking the real friction points.
The everyday headaches of keeping these massive machines from, well, burning down the buildings they serve.
So to really get the philosophy of NFPA 37, we kind of have to compare it to another code everyone knows, right? NFPA 110.
Yeah, NFPA 110 is the standard for emergency and standby power systems, but their goals are completely different.
How so? Like, what's the fundamental difference there?
Well, NFPA 110 is entirely focused on electrical reliability. It asks, when the grid goes down, does the engine start? Does the transfer switch work?
So it's basically making sure the lights actually come on.
Exactly. It's an operational mandate. It assumes the grid will fail, and its job is to guarantee the engine runs.
Okay, so if NFPA 110 is the personal trainer making sure the heart keeps beating, NFPA 37 is, what?
It's the cage, keeping the tiger from eating the spectators.
Oh, wow. That is a dark view of the situation.
But it's true. NFPA 37 assumes the engine itself will eventually fail. And when it does, it assumes it will cause a severe fire.
So it doesn't care if the hospital gets power.
Not at all. Its only mandate is containment and isolation. It just wants to make sure that when a fuel line ruptures and sprays diesel onto a hot exhaust manifold, the hospital itself doesn't catch fire.
Man, that's a stark division of labor. So at what point does this hazmat team actually step in? Like, what triggers NFPA 37?
The entry point is 15 kilowatts. Anything rated above that triggers the standard.
Wait, 15 kilowatts? What does that actually look like in the real world?
It's pretty small. Like a 10 kilowatt portable generator you buy at a hardware store is exempt.
Right, the kind you'd use on a job site.
Yeah, but a 15 kilowatt or say a 30 kilowatt standby generator sitting behind a small office building or a convenience store, that triggers the full weight of the standard.
So suddenly you're bound by all these crazy clearance and ventilation rules just for keeping the office fridges running.
Exactly. The moment it's hardwired into a permanent structure, you are in NFPA 37 territory.
Okay, so let's walk through this chronologically for you, the listener, starting with the site plan, because before we can pipe any fuel, we have to figure out where to physically put the thing.
And this is the very first major headache for designers, the geography of risk.
According to the Consulting Specifying Engineer source, there are 4 permitted locations, right?
Yes, you can do a dedicated indoor room, which requires a fire resistance rating. You can do a detached adjacent structure, a rooftop, or outdoors on grade.
Outdoors seems like the obvious choice. Just pour a concrete pad out by the loading dock and you're done.
You'd think so, but the distance rules dictate absolutely everything.
Right, the baseline rule is a 3-foot clearance to any combustible walls. That doesn't sound too bad.
3 feet is manageable, but real estate is expensive, especially in urban environments.
Yeah, I mean, architects want to push that generator as far into the corner as possible to save parking space.
Exactly. But 3 feet is just the baseline for walls. The real nightmare is building openings.
Openings, so like doors and windows.
Doors, windows, and crucially, HVAC fresh air intakes. The code mandates a 25-foot separation from the generator to any opening.
25 feet, that's huge. Why so far?
2 reasons. First is radiant heat. If the generator is engulfed in flames, a window 10 feet away will just shatter from thermal shock.
And then the fire just walks right into the building.
Exactly. The second reason is carbon monoxide.
Oh, right, the exhaust.
Yeah, if you park a diesel engine 5 feet below a hospital's fresh air intake, you are pumping lethal exhaust directly into the patient wards during a power outage.
So if I'm an engineer in downtown Chicago drawing a 25-foot radius around every door and lever, I might end up having to put the generator in the middle of the street.
Which is why we have the most heavily scrutinized loophole in the industry. Exception 2.
Oh, exception 2, the battlefield. Walk us through how this loophole actually works.
So exception 2 says you can completely bypass those minimum distance rules, the 25 feet and the 3 feet, if you need two conditions.
Okay, what's condition 1?
The generator have to be in a weatherproof enclosure made of non-combustible materials.
Easy enough. Most commercial units come in steel or aluminum boxes anyway. What's the catch?
Condition 2. It must be demonstrated that a fire inside that enclosure will not ignite combustible materials outside of it.
Demonstrated. That sounds incredibly subjective.
It is entirely subjective. The code gives no specific parameters for how to prove this.
So how do engineers actually prove it to the authority having jurisdiction, the AHJ? Do they, like, light a prototype on fire in a parking lot?
I mean, essentially, yes. They rely on third-party laboratory fire tests provided by the manufacturer.
But if I'm a fire marshal, I'd hate that. A lab test doesn't account for, a blizzard with 40-mile-per-hour winds.
Fire marshals do hate it. Think about the variables. Does the test assume the engine's massive cooling fan is running?
Oh, right. Because a massive fan might actually blow the fire out.
Or at least move so much ambient air that the metal box doesn't get that hot.
But what if the engine is off? Like a block heater shorts out at 2 a.m.
That's the nightmare. The fan is off, the box is sealed, and it just bakes. The internal temperatures skyrocket.
And the test doesn't know what the adjacent building is made of. The enclosure might max out at 400 degrees, but if the building next to it has foam insulation...
It could melt or ignite.
Yep.
Exactly.
So what's the actual advice for engineers here? Just fight the fire marshal?
No. The advice from experienced designers is to avoid exception 2 whenever humanly possible. Maintain a physical 5-foot separation.
Because 5 feet is something you can measure with a tape measure. It ends the argument.
Exactly. It changes a subjective debate into an objective fact. It keeps your permits from getting delayed.
Okay, so let's say we've got the site placed, the unit is bolted down, now it needs to breathe. Let's talk about the lungs of the beast.
Ventilation is critical. An engine starved of air is a catastrophic hazard.
So, looking at the physics, a typical 250 kilowatt diesel needs a wild amount of air. The numbers here are crazy.
Yeah, a 250 kilowatt unit needs roughly 4,500 to 4,500 cubic feet per minute of cooling air.
Just to give you a sense of scale, 4,500 cubic feet is like emptying out a standard 2-car garage every 60 seconds.
Every single minute the engine is running, yes.
So how do you physically move that much air into a fire-rated room?
You have to cut massive holes in your fire-rated walls for louvers.
But you can't just leave a hole in a firewall.
Right, so they are motorized. Intake louvers are mounted low to draw in cool air, and discharge louvers are mounted high to vent the hot air.
That makes sense thermally. Heat rises.
But this leads to a massive, everyday operational failure point, the louver trap.
The louver trap. This is where the electrical design ruins the mechanical design, right?
Exactly. These motorized louvers need power to open. When utility power fails, designers often wire the levers directly to the generator's start circuit.
Because the generator is the only thing making power.
Logically, yes. But what if the actuator gets stuck? What if ice freezes the louver shut on the outside wall?
Oh, man. So the engine starts, but the louver stays closed.
And then you have an engine running at full RPM inside a sealed concrete vault.
It would consume all the oxygen in seconds.
Seconds, it creates a massive negative pressure vacuum, the heat spikes instantly, and the engine's internal sensors trigger an emergency shutdown to keep it from melting.
So it kills the power to the hospital right when they need it most, all because a mechanical louver got stuck.
Exactly. Which is why best practice dictates fail-safe actuators. They should be held closed by electricity and use a heavy mechanical spring to snap open when power drops.
That way, if the power fails or the circuit breaks, the spring forces it open no matter what.
Right. It's a simple mechanical override to a complex electrical problem.
Okay, so we've got the air coming in.
Yeah.
But we also have superheated air going out, the exhaust.
The exhaust is the most acute thermal hazard in the room. The Anvil Fire blog goes into great detail on this.
Yeah, they noted that exhaust manifolds run between 600 and 900 degrees Fahrenheit.
900 degrees is well above the auto-ignition temperature of most building materials.
Like wood framing. If a 900-degree pipe touches a wood roof deck, it doesn't even need a spark, right?
Right. Through a process called pyrolysis, the heat conducts into the wood, dries it out completely, and eventually it just bursts into flames.
So you can't just punch a hole in the roof and run the pipe out.
Absolutely not.
Yeah.
NFPA 37 requires ventilated metal thimbles for any penetration through combustible assemblies.
A thimble, like a sleeve around the pipe.
Yes, a double-walled metal sleeve. It creates an air gap between the hot exhaust pipe and the structure. Air is actually a fantastic thermal insulator.
How big of an air gap are we talking about?
For a combustible roof, the thimble has to extend 9 inches above and below the roof and be 6 inches larger in diameter than the pipe.
So a 6-inch pipe needs a 12-inch thimble. That's a 3-inch air gap all the way around.
And for a combustible wall, it's even stricter. It must be 12 inches larger than the pipe.
Wait, really? Why is a wall stricter than a roof?
Because horizontal penetrations trap heat differently. In a roof, thermal convection carries the heat up and out. In a wall, it can pool and radiate outward.
Wow. So structurally, you have to frame out massive holes just to get this pipe out of the building?
It takes up a lot of real estate.
Yeah.
And getting the pipe out introduces another issue: fluid dynamics and back pressure.
Right, because the engine is basically an air pump pushing exhaust out.
If the pipe is too long or has too many bends, the engine struggles to push that gas out. That resistance is back pressure.
And if there's too much back pressure, the hot gas stays in the cylinder, right?
Yes, it displaces the fresh air for the next cycle. The engine runs hotter, loses efficiency, and can even blow out its exhaust valves.
So what's the common mistake here? Just using the same size pipe as the manifold connection?
Exactly. If the manifold is 4 inches, contractors often just run 150 feet of 4-inch pipe to the roof.
Which is a disaster.
Absolute disaster. The rule of thumb from NFPA 20 is that for runs over 15 linear feet, you must step up the pipe by 1 size for every additional 5 feet.
So a 4-inch pipe becomes 5 inches, then 6 inches, just to prevent that friction.
Yes, though modern manufacturers have software to calculate this precisely now, the software always overrides the rule of thumb.
There is one thing about the exhaust that feels totally counterintuitive to me. Wrapping the exhaust in insulation.
Ah, yes, the thermal blanket.
Yeah. I mean, if the exhaust is 900 degrees, wrapping it in insulation seems like putting a winter coat on a radiator. Doesn't that just trap the heat in the engine?
It's a great question. You have to separate the engine cooling from the hazard protection. The engine block cools itself with its liquid coolant and the radiator.
Assisted by that 4,500 cubic feet of room air.
Exactly. The exhaust pipe, however, has already left the engine block. It's radiating infrared heat into the room.
Oh, so it's not hurting the engine, it's threatening the room.
Right. If a technician brushes against it, it's instant third-degree burns. If someone leaves a cardboard box nearby, the radiant heat will ignite it.
So the blanket keeps the surface safe to touch and forces all that thermal energy to travel outside the building?
Precisely. It traps the heat in the gas stream itself.
Okay, so we've given the beast space, we've given it air, we've routed the exhaust, now we have to feed it.
The most volatile part of the system,
Right.
pumping highly flammable liquids or gases directly into a vibrating hot machine.
This is where NFPA 37 intersects with NFPA 30, right? The liquids code.
Yes, and the regulations are incredibly strict, starting with material bans.
What's banned?
You cannot use PVC, you cannot use copper, and no plastic flex hose for primary diesel piping.
Wait, no copper. We use copper for natural gas in houses all the time.
We do, but NFPA 37 explicitly bans low melting point materials for critical seal components.
Because if there's a fire.
Copper loses its tensile strength and sags at relatively low fire temperatures. If a small electrical fire hits a copper fuel line, it'll melt,
And then you have a pressurized line dumping hundreds of gallons of diesel into the room.
turning a small contained fire into a massive pool fire. That's why the standard is Schedule 40 black iron pipe.
With welded or threaded joints. Because iron will survive the initial fire long enough for the suppression system to kick in.
Exactly. The only exception is a specialized listed vibration connector right where the rigid pipe meets the vibrating engine block.
Now, diesel behaves like a liquid. It pools, it drops. But what about gaseous fuels?
Gases require a totally different strategy. For natural gas, you need a highly regulated gas train.
The gas train, that's the sequence of valves and regulators, right?
Yes, isolation valves, regulators, and crucial automatic safety shutoffs. If the engine stops, those valves slam shut instantly.
But the source has made a really big deal out of propane versus natural gas.
Propane is uniquely dangerous because of its vapor density. Natural gas is lighter than air. If it leaks, it floats up to the ceiling and vents out.
But propane is heavier than air.
Much heavier. If a propane line leaks indoors, the gas cascades down the side of the engine and pools on the floor.
Like invisible water filling up the room.
Exactly. It settles into trenches and drains, creating a highly explosive mixture just waiting for a single spark.
Which is why indoor propane engines mandate low-level gas detection.
Yes, sensors mounted right near the floor. It's a specific requirement for heavier-than-air fuels.
Let's talk about storing all this fuel, specifically diesel day tanks.
Ah, the day tank limits. This is where it gets legally interesting.
So a day tank inside a shared building space is capped at 660 gallons. In a dedicated fire-rated room, it's 4,320 gallons.
That's the baseline rule. But Chapter 6 contains a massive loophole.
The subjective exception, as the consulting specifying engineer article called it?
Yes, the code states that tanks of absolutely any size are allowed indoors if the room has, quote, suitable fire detection, fire suppression, and containment.
Wait, suitable? That's a terrifying amount of leverage for an inspector.
It really is. By that wording, you could put a 5,000-gallon tank on the third floor of an office building, as long as you convince the AHJ it's suitable.
But what one fire marshal thinks is suitable might be totally different from another.
Exactly. One might just want standard sprinklers and a concrete curb.
Yeah.
Another might demand a fully flooded chemical clean agent system and a foam purge system.
So how do engineers handle that ambiguity?
By never designing in a vacuum. If you're going to use that exception, you have to bring the fire marshal into the conceptual design phase. Get their approval before you pour concrete.
Because if you wait until final inspection and they reject your suitable system, you are financially ruined.
It would be devastating. And speaking of fuel logistics, we have to talk about the EPA's 10% underground rule.
Oh, this was wild. The Emergency Power Generator Underground Storage Tank rules, or EPG-USTs.
It's a classic trap for designers where environmental law overlaps with fire code.
So the rule is, if 10% or more of the total system capacity is underground, the whole thing counts as an underground storage tank.
Triggers full federal compliance, yes.
Let's break down the math on this because it's sneaky. Say a hospital has a 20,000-gallon above-ground tank in the yard and a 1,000-gallon above-ground day tank on the roof.
So far, 0% underground storage.
But to connect them, the contractor runs the fuel supply and return lines underground across the parking lot.
You have to calculate the volume inside those pipes. A 4-inch pipe holds about 0.65 gallons per foot.
So if you have thousands of feet of pipe running back and forth, you could easily have, say, 2,600 gallons of fuel trapped inside the pipes.
And 2,600 gallons is more than 10% of the total 23,600-gallon system.
So by just burying the pipes to make the parking lot look nice, you've accidentally turned your above-ground tanks into a federally regulated underground facility.
Exactly. Now the owner needs double-walled piping, leak detection monitoring, annual EPA testing.
Yeah.
All because of the pipe.
The pipe literally became the tank mathematically.
It requires engineers to really look at the spatial layout holistically. You can't just look at the engine alone.
Okay, so despite all of our clearances and thimbles and iron pipes, NFPA 37 knows the system will eventually fail and catch fire.
Yes. And when it does, we move from containment to active suppression.
For indoor rooms, the baseline is passive protection, a 1-hour fire-rated vault.
Or a 2-hour vault for mission-critical facilities, like data centers or hospitals.
But walls just hold the fire in. We have to actually put it out. Which brings us to the suppression showdown. Clean agents versus sprinklers.
Data centers and hospitals absolutely dread water damage.
Right, because if a standard sprinkler head pops over a 2-megawatt generator, it's dumping gallons of water onto high-voltage electronics.
The water shorts out the alternator, ruins the digital controls, and if the engine breathes it in, it hydrolocks the cylinders. The fire is out, but the multi-million-dollar machine is garbage.
So they lean toward clean gaseous agents like FM200 or Novec 1230.
These gases flood the room, interrupt the combustion reaction, and then evaporate completely. Zero residue. Zero electrical damage.
Sounds perfect. What's the catch?
The engineering catch in NFPA 37 is the 20-minute hold time rule.
20 minutes? Why is that so hard to achieve?
Remember those massive levers we built to move 4,500 cubic feet of air?
Oh, right. We literally designed the room to be completely porous.
Yes. So when the fire alarm trips, the engine has to shut down, the fuel valves have to close, and those massive louvers have to slam completely shut and form an airtight seal.
And if they don't seal perfectly?
The suppression system dumps tens of thousands of dollars of clean agent gas into the room, and the residual airflow just blows it right out into the parking lot.
The fire just keeps burning.
Even if they do seal, there are tiny microscopic leaks everywhere. Conduits, door frames, The gas slowly escapes.
But why 20 minutes? Why can't the gas just put the fire out in 1 minute and we're good?
Thermal inertia. A heavy diesel engine block and a 900-degree exhaust manifold hold massive amounts of stored heat.
Oh, I see.
If the gas leaks out after 5 minutes, fresh oxygen rushes back in. The exhaust is still at 700 degrees. The fuel is still on the floor.
Boom. Instant reignition.
Exactly. The temperature is still above auto ignition, and now your suppression gas is gone. You have a free-burning fire.
So how do you even prove a room can hold gas for 20 minutes?
You have to do a room integrity fan door test. They seal a massive blower fan into the doorway, pressurize the room, and calculate the exact leakage rate.
Sounds like a nightmare for contractors.
It is. They often spend weeks caulking every tiny crack just to pass the test, which is why many engineers actually advise clients to just accept the water risk and use standard sprinklers.
Wow. So you intentionally sacrifice the equipment to guarantee the building survives.
It's a calculated compromise.
Yeah.
Water provides infinite cooling, prevents reignition, and you don't need an airtight room.
To bring all this theory into the real world, I want to talk about that case study from EPC land.
Ah, yes. The commissioning inspection. It's a perfect example of what goes wrong in the field.
So the engineering team shows up for a final inspection on a new facility, and they find the outdoor generator is installed only 3 feet from a combustible wood-framed wall.
Which is a direct violation of the 5-foot clearance rule we discussed earlier.
But it gets worse. The manual fuel shutoff valve was located entirely inside the generator's weather enclosure.
Think about that geometry. The generator's too close to a wood wall, and the valve to turn off the fuel is trapped inside the hazard zone.
If a fire starts in there, the flames are threatening the wall, and no human is going to reach into a burning steel box to turn off a valve.
The day tank will just continuously feed the fire until it's empty.
Normally, the fix would be, hey, contractor, pick up the 30,000-pound generator and move it 2 feet back.
But the concrete is cured, the underground conduits are poured, the fuel pipes are welded. Moving it is agonizingly expensive.
So what did they do? The article says they got creative.
This is pragmatic engineering at its finest. They couldn't move the heat source, so they changed the properties of the wall.
They built a 1-hour fire-rated masonry brick barrier in that 3-foot gap between the generator and the building.
A thermal shield. The radiant heat from a fire would strike the brick, not the wood siding. It neutralizes the proximity hazard.
Basically, they built a fire-rated moat, but what about the tracked valve?
They couldn't move the valve on the engine, so they went upstream. They intercepted the fuel supply line before it reached the enclosure and installed a remote manual shutoff.
So a responder can cut the fuel from a safe distance.
But they added redundancy. They also installed a solenoid-controlled automatic valve tied directly to the building's fire alarm.
Oh, that's brilliant. So if the heat detectors trip, the alarm fires, the solenoid drops closed instantly.
Mechanical fuel cutoff before a human even arrives. The brick wall holds the heat at bay while the fire starves itself out.
It's essentially an automated drawbridge over that fire-rated moat. It proves that code compliance isn't just following rules, it's creative problem-solving when someone else messes up the site plan.
Exactly. You achieve the fundamental goals of NFPA 37 containment and isolation without completely rebuilding the site.
So, for the firefighting engineers and facility owners listening, the big takeaway is that NFPA 37 is a system of redundant safeguards.
Distance, ventilation, metallurgy, suppression, all working together to isolate inevitable mechanical failures.
It's truly fascinating. Before we wrap up, I want to leave you, the listener, with a final provocative thought.
The future of emergency power.
Everything we've discussed today, NFPA 37, the iron pipes, the ventilation, is built around the physics of internal combustion. Liquid diesel, pressurized gas, 900-degree exhaust.
But the industry is shifting rapidly.
Exactly. Facilities are installing massive lithium-ion battery energy storage systems, or BESS, right next to or instead of these traditional generators.
And lithium-ion fires behave entirely differently.
When the fuel isn't a liquid in a pipe, but a chemical reaction in a cell that is prone to thermal runaway and actually produces its own oxygen as it burns, the rules change.
Traditional suppression, like water or clean agents, struggles against thermal runaway.
So how will the physical boundaries of engine rooms evolve? Will a 1-hour brick wall do anything against a prolonged lithium-ion fire? Will that 5-foot clearance rule survive the next decade of engineering? Or are we going to have to write an entirely new playbook for the power ecosystems of tomorrow?
It's the next great challenge for fire protection engineers.
Keep that reality in mind when you're reviewing your next site plan. Thanks for joining us on this deep dive.